Good morning, class. How's everybody doing today? Hope you guys are doing well. I know I'm doing okay. Really, that whole business of getting an extra hour's sleep over the weekend is just like, man, I wish we had that every weekend. I know it, doesn't work, mathematically, but it would still be nice, you know? Man. So, how did everybody find the test? Was the test okay? Did you find the test okay? Is the class average fake? I don't know. Mark's really on top of things. And, crazy how quickly he gets stuff out sometimes. So let's take a look at the class average for the test. Just out of interest. Manage grades. Do 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 do. Do 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 do. Midterm 2. View stats. Ba-do-ba-ba-ba-do. Oh, it was way too easy. Oh, man. No, okay, so that's quite a high average, actually. Very few people failed, so there you go. Neat. All right, yeah. No, that's not a fiction. That won't be a fiction. Oh, hey, Mark's here today. Awesome. Okay. Oh no, there are a couple of MSAFs. I haven't had the time to. I haven't had the time to send you the MSAFs yet, Mark. But that will happen. How much of Southern Ontario ended up getting snow? We got a little bit of snow. It didn't actually stick, and that's interesting because when you live, if you're aware of the local geography of Hamilton, because of the escarpment, everything that's below the escarpment is it lags behind by 2 weeks in terms of the amount of winter weather that you get versus pretty much everywhere else. It's just milder. That's why this region of Ontario is sometimes referred to as the Banana Belt. But yeah, no, we got a little bit of snow, but not too much. Heard that today they were calling for flurries in Burlington, though, which is just across the water, so we shall see. It's a cold one today. Although, by the end of the week, we'll be seeing temperatures back in the high teens. So if you have any bulbs to be planting for spring, this will be the week to be doing it in. On to you. Yeah, anyway. Right, newscaster. Anyway, alright. So, let's talk testing and exceptions. And maybe, oh, no. I want my special thing open with document viewer. There we go. That's better. Coolio. All right. So, good. Hamilton is called the armpit of Canada. Is that because it's so humid and warm? Grand Bend, oh. Press F to pay respects for Grand Bend. Alright. Everybody should appreciate Mark and all of the work he does for this class. He does even more work for this class than I do. Snark. Anyway. Testing and exceptions. Let's get right into it, because we're a little behind. So, bugs. Likely, at this point in time, you have run into bugs. So, let us formulate a more technical definition of what constitutes a bug or a glitch in software. They don't really call them glitches anymore, but it's kind of like a bug is your fault and a glitch is like the computer's fault. That's kind of the you know. Anyway, so we are tasked to write a function maxProduct that takes as input a base 10 number s represented as a string and outputs the product of the 12 adjacent digits that have the greatest product. So you can sort of imagine it like you have a sequence of decimal digits and you are thinking about a window in that string that is 12 digits long. And whatever window, you move the window along through the string, and whatever window has the maximum value when you multiply all of the digits that are in that window together, that is the max product. So that's what we're finding here. Define max product. Max product equals 0. For I in range of the length of s minus 12, product is equal to 1. For j in range 12, product times equals the integer conversion of the digit at index I plus j. If the product is greater than the max product, we set max product equal to the product that we just calculated. And at the end of all that, we return max product. There is a bug here. I will ask... to the idea of increasing Mark's salary, or even my own. No, that's set by the union. So, we... If I were an economist, I would say something like, the union has removed our right to negotiate our wages. But, you know, the union would say, we negotiate your wages on behalf of you, with greater negotiating power. Anyway, so, oh, jeez, I hate it when I do that. Come on. So, the bug, if you run this, well, there are slides that'll show us what the bug is. So, how could you detect bugs? What are the procedures for detecting bugs? Because, you know, it's important to be able to find the bug. You have to be able to find the bug before you can fix the bug, right? So, number 1, make some test cases with known correct answers to see if you get the right answer. This is called having a golden model, or having an oracle. Having another person independently implement the function and see if they get the same answer. This is less reliable than having an oracle. Having another person read your code to see if they can find any flaws. This could have, you know, I'd say that's better than the second one, but still not as good as having an oracle. The only problem is sometimes it's difficult to have an oracle. Sometimes if the thing is sufficiently complicated. So, the goal of testing is to determine whether a program works as intended or not. Debugging is the process of trying to fix a program that you already know has a bug. So, we test to see if there are bugs, and we debug in order to remove bugs that are found. I am obligated at this point in time to share with you the reason we call it debugging. Some of you will probably already know this story, but back in the ancient days of computing, back in the 1950s and 60s, when a computer took up, you know, an entire room, an entire classroom, or the entire floor plan of my house, probably. What a computer consisted of was a large number of vacuum tubes. Vacuum tubes were the thing that we had that could simulate an electric switch prior to the development of solid-state electronics. It sort of went relays with magnetism, which is basically a solenoid that attracts or repels a magnet that opens or closes a switch, so you can run a switch electronically that way. It's good, but it requires actually a reasonable amount of power to be able to generate that amount of magnetic flux to be able to open and close a switch. Vacuum tubes, I'm not actually sure how vacuum tubes work precisely. Never studied them, but they were sort of a light bulb-like implement that performs the same functionality more reliably than a relay. And then you had solid-state electronics, which do everything in silicon in a way that can't be interfered with, and can be hyper-miniaturized on the level of, like, atoms, number of atoms of thickness these days. So anyway, back in the ancient days of computing, you had these computers that were these large, cavernous spaces that had lots of access, because when you had a computer like that, you would often have to, for example, replace a vacuum tube that had burnt out by manually going into the computer and replacing it with a replacement vacuum tube. So what would often happen in these things is that you would get these creepy crawly critters that would enjoy living inside of the computer, because, you know, spiders like to be inside of things, and, you know, other sort of creepy crawlies, even things like mice and small mammals. So what would happen sometimes is a bug would make contact with its body across two electrical contacts inside of the computer. And sometimes what would happen, if they were, you know, opposite voltages, you'd have bridging of electrical power through that animal. You would kill the animal instantly, and if the animal was fried in just the right position, that would actually bridge the electrical contact. And that might result in your computer performing things weirdly. So, in the 50s and 60s, the process of debugging was actually, the manual extraction of dead bugs from a computer. So that's why they called it debugging. Or, you know, this circuit's got a bug, that circuit's got a bug. It's just, you know, it's nomenclature that holds over to the present day. Yes. You guys have nailed the bug in the previous program. So, here is the testing and debugging cycle. Number 1, you write your program. Number 2, make sure the compiler/interpreter can execute it. This is checking that your program is constructed correctly in terms of syntax. Have you followed the programming language's grammar? Number 2, you test to determine if it works as intended. If it does not, you identify the bugs. You fix the bugs in the source code, and then you recompile, and then I would technically move this arrow to this one, because anytime you modify the program source code, there is the possibility of you introducing syntax errors, and you have to compile it in order to test it anyway. So, but yeah, anyway. So that is, generally speaking, you sort of stick in this bottom part of the loop until all of your tests come out. And you guys are already well familiar with this procedure, because that's what you've been doing on the assignments all this time. At least if you have been doing the assignments in a manner that has been resulting in reasonable grades. What you have been doing is you have been writing your assignment function, then you run the test cases that we provide you, and if the test cases work out, then the problem is considered solved, you know. And then it's subject to more rigorous testing as of the hidden test cases. But anyway, so generally speaking, testing methods fall into two categories. We have whitebox testing, and we have blackbox testing. So the difference between white and black boxes, it's kind of a misnomer, because it should bespeak opacity rather than, you know, the colors white and black. When you hear white box testing, you should think clear box testing. And if you hear black box testing, you should hear opaque box testing. The only problem is, you know, clear and opaque don't roll off the tongue, I guess, sufficiently well. So with white box testing, these techniques rely on you being able to see the program's source code. So these are techniques such as static analysis and, does my code adhere to various programming standards? Python is not really a language where you are super concerned about programming standards. Probably primarily because Python is a language that it tries to limit the number of different ways that you can do something. And a lot of things are provided for you. A lot of the sort of behind-the-scenes work that it's really important to get right is in the form of library functions in Python. So there's not as much adherence to programming standards as you would see in a programming language like C. In C, everything is very low level, and there are, where in Python there's 100 million ways to do any particular thing. In C, there's 9,470 billion ways of doing any particular thing, most of which are very, very difficult to read. Like, for example, you don't use goto statements. If you use a goto statement, that is considered incorrect even if the program works, because goto statements are universally considered to be a terrible solution to any problem, unless you're programming in assembly. But anyway, so that's Whitebox Techniques. Analysis of the code itself. Blackbox Techniques are what we have been doing with the assignment so far. This is, we provide specific inputs and we watch for specific outputs, known correct outputs. The advantage of this technique is that it does not rely at all on knowledge of the source code of the program itself. You guys can implement your function however the heck you want. As long as the test cases are satisfied, then it is considered to have passed the test. That's black box testing. Both of these require a clear specification of the program's expected behavior. Specifications, very important. When we provide you test cases, we are providing you specifications. So, black box techniques do not rely on knowing the program's source code. They only rely on the ability to put input in and see what the corresponding output is. This focuses on the development of test cases to see if the actual output matches the expected output for a given input. So, in your test case, you have the output that you want, and you are running the program to see if the output that you get is the output that you want. The problem, of course, with this style of testing is that it is impossible to exhaustively test a program. There are, you can imagine if you were to test, two integers, a function that takes two integers and produces an integer. What are you going to do? Test every single possible integer combination of inputs? Probably not. If you're dealing with 32-bit integers, then that is 2 to the 64 possible inputs, because that's how this works, which is 1.8446 times 10 to the 19 possible combinations of inputs, which is problematic if you want to test exhaustively. Let's assume, generously, that you could perform 1 million tests per second. Divide by 60 seconds in a minute, divide by 60 minutes in an hour. 11. 60 minutes in an hour. This calculator's so old, the buttons are getting 60. Sticky. 24 hours in a day, 365 days in a year. So, to exhaustively test 64 bits of input data would take 584,855 years. So exhaustive testing isn't possible. Generally speaking, that's why when we design black box tests, we design them such that they are representative of categories of inputs. That's why we test edge cases and we test normative cases. Edge cases typically represent, well, anyway, we'll talk about edge cases. Questions? Okay. So, software design principles. These things make it easier to test and work with the code that you're producing. And believe me, once your code reaches a certain size, you're going to want that. Oh my goodness, am I using... Oh my goodness. I'm not using my little... I'm not actually using this microphone. Let's try this. Maybe I've been quiet this whole time. Maybe you've liked that. That's this one. That's this. Testing, testing, 1, 2, 3, testing, testing. Testing, testing, testing. There, that's a little better, right, guys? Actually, tell me if that was better or not. Good. Okay. Anyway, so modularity and decomposition. This means that you can take your program and you can break it down into different pieces that are responsible for more specific tasks. So when you think about an algorithm, it's kind of like, well, yeah, it's the process of writing a function. Later, in our next topic, in our next set of slides, we're going to talk about an additional mechanism for modularity, decomposition, and abstraction, which is called classes. And classes are just a mechanism for packaging together data with functions that operate on that data, in the most basic form. So, but for now, we can think about this mostly in the context of functions. If we have a series of operations that we know will be repeated frequently, we can write a function for that. And when we write a function for that, that means that that piece of the code can be tested in a black box sense independently of the rest of the program. This means that we can verify the subcomponents of our software system, and then we can have a better assurance of correctness when we plug all of those modules together in order to create the larger body of software. So, modularity and decomposition. This means that a program is broken down into parts, functions, or classes that are 1. Reasonably self-contained, 2. Achieve a clear purpose, and 3. Can be reused. Abstraction. A component or a function or a class of a program can be used without knowing how it achieves its goal. It is not necessary to know how a function calculates what it calculates in order to use that function. It's not necessary for you to know how print actually prints something. All you need to know is that print prints something, and that printing is defined as writing a series of characters into standard output. So, the goal there, if you've written a function, it allows you to abstract some part of the solution to the problem. And you're kind of implicitly doing this when you, write a program and do, okay, this part does this, that part does that, that part does that. You're kind of doing the same thing, just not, designating them as separate functions. But when you write a function, so the problem with software development, to some extent, is keeping the entire program in your head at once. So once you have mastered the ability to abstract things, you will have mastered the ability to say, okay, I don't have to think about how this is implemented anymore. I'm just going to use it. And that vastly simplifies the amount of mental work that you have to do in order to write a program, which is a good thing because sort of at the extreme end of things, computer programs can be very, very difficult and complicated. Computer programs are among the most complex thing that human beings have yet created. So, black box testing of big programs. Modularity enables better black box testing. We wish to develop test cases for every function in a program to ensure that each individual function works as expected. This is called unit testing, because we are testing the units. We then develop tests to see if the program as a whole is working as expected. This is called integration testing, because it's testing the integration of the units. We also have a type of testing called regression testing. When a bug is fixed, and then later more source code changes are made, those changes may reintroduce the same or similar bugs, especially if the fix that you came up with for your bug was not a good fix. So when you have written a test case for a specific bug, you should keep that test case around. You should have two of them. You should have one test case that should fail if the bug is present, and one that passes if the bug is fixed. So, if you keep both of these around and run them every time you run all of your test cases, then you will be able to spot if the bug has been reintroduced by a more recent change to the source code. This is a manner in which we can detect regressions. A regression, in this sense, is a bug that is reintroduced. So there we go. Continuous integration testing. It is possible to create a testing framework that runs all of your tests every time you make a change to the source code. Or at the very least, every time you submit your changes to the organization's code repository. You guys in computer science will at some point run into the idea of a code repository. For those of you who don't know what a code repository is, a code repository is it's like a meta program. It's a program that keeps track of changes that you make to a programming project that you're working on. So a popular one on the internet these days is Github. Github has its own community, which is a very nerdy community indeed. GitHub was recently acquired by Microsoft. So basically, how code repository or repo works is you're working on your code, and then you're working on your code for your standard work day. At the end of the day, when it's time to go home, or more frequently, you submit the code that you've worked on to the repository. The repository keeps time-stamped versions of the history of the code you've been working on. So, if you were just having a really bad day on Thursday and you just completely messed everything up, you can actually use your repository to roll back the code to a point where it was less screwed up, and then you can continue on from that point, sort of discarding your changes in a non-destructive manner. You can also always go back to the more forward iteration if you decide that that actually was the best approach. It's just the problem is terrible. So, repos are really good. They are a must for any project that is either sufficiently large or has more than one person working on it. So, here is an example of integration testing that was on a GitHub page owned by the person who put together these slides. It was not me. So, we have... This is what GitHub looks like, basically. And when you can configure GitHub so that it runs specific tests on your code anytime anytime your code is committed to the repository. It automatically runs the tests, and it'll tell you if the tests come out as failures, and that way you can keep on top of whether or not the code is working or not, which is always a good idea. There we go. Okay, I'm going to take some questions. We're making good time. Is quick check in the Haskell a code repository? I'm not sure. You guys think it was better before? You think this... So this microphone... Okay. Okay, alright. So be it. I'll use my laptop's mic from now on, then. I guess I don't even need these, then. Jeez. Alright. Ugh. We have... My head is now free of the things. Maybe I won't shout quite so much now because I can't, like, my ears aren't blocked. All right. Testing, 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 testing. Okay. All right. I don't know, my head looks small without them. Anyway. All right. Yeah, don't worry about not having the time to learn Git. It's not too bad to learn, and also, you're going to have to learn it, I'm pretty sure, for one of your classes or another next semester anyway. So, there you go. Assuming you're in comp sci, which there's, about a 50% chance. But anyway, so, developing test cases. We want to cover all of the different types of input that could be provided. We need to take into account edge cases when the input is at some extreme or might require special handling. So good edge cases are things like 0, especially if your algorithm involves division. You want to make sure that no input combination that might lead to a div0 error is not being handled. For numbers, the types of classes of tests you want to do are things like positive and negative numbers, 0, 1, odd numbers, even numbers, prime numbers, composite numbers, etc., etc. For strings, you always want to test things like an empty string or a singleton string. A singleton string contains one character. For lists, try the empty list, try a singleton list. For subsequences, try the sequence at the beginning, sequence at the end. So, going back to our max product example, the input string is a minimum length of 12 digits. The max product is minimally 0. The maximum possible value is 12 nines multiplied together. So, we should have a substring corresponding to the max product, which starts at the beginning of the string, and one that starts at the end of the string, to make sure that we're dealing with our positional edge cases correctly. The edge cases that you should always be most concerned about with are positional edge cases in lists and arrays and that sort of thing. Anything that you have to index. It's very easy to get an off by 1 error when you're tracing through a list or an array or something like that, and they're easy to miss. So you want to have a case where those edges are exercised. So we would have a substring corresponding to the max product at the beginning of the string and at the end of the string, and maybe somewhere in the middle as well. So let's take a look at this string as a test. In theory, this would be the maximal subset. Assuming that was 12 characters, it looks like, okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So this would be the maximal subset. This would be like the correct answer. If we actually test this, we get this value. However, if we do the calculation out by hand, we'll find that what the expected correct value is this one, which you can see those are different. So we have a bug in the system. So when you create the test case, and this is kind of an important technical point, it's important not to create the test case with the program that you're testing. You always want that test case to come from some different assumed correct source. So, for example, when we create an assignment or a test, very often the test cases that we produce and give to you are generated from a sort of the solution that we develop to the problem, right? So, generally speaking, the procedure for coming up with a new question is we have some idea of what we'd like the we would like the question to be. We write the program, right? Well, pardon me, back up. Once we have an idea, we type that idea out, give it some description. We then write the code that solves the problem, refine the question according to the expected solution, and that's the process where we give hints like, this part's difficult, so just keep that in mind. And then once we are finished with adjusting the question, we feed some inputs into our example code, get the outputs from that, and then generate the test cases from there. So in the case of our max product, since we know there's a bug, we can start playing with things a little bit to see where the bug might be. In this case, it's easy enough to verify the test case using a calculator. Calculators are convenient, but not always possible. So, in order to see if the bug is, like, why the bug is happening, we can play with the inputs a little bit. If the bug is happening because the string, because the selected bracket is at the end of the string, if we make it no longer at the end of the string anymore, we may come to some conclusions about why the data is being messed up. So in this particular instance, the problem is that we're subtracting 12 here when we should be subtracting 11, as some of your colleagues noted in the chat. This is called an off by 1 bug. So the problem was that this final case was never being evaluated. Because we were subtracting 1 more than we should have, we were always 1 down from, like, we would never test right to the end. We would always test to 1 before the very end of the string. So, if we change it to 11, then everything works. So, let's talk about whitebox techniques. I know I'm moving quickly, but I have, we got ground to cover here. So, whitebox techniques. Whitebox techniques rely on knowing the program's source code. So, these could be something like a code review, which is a process where 2 or more developers visually inspect program code, typically several times. They are checking for programming best practices, i.e., don't use any go-to statements and stuff like that. They're looking for potential inefficiencies, and they're looking for common vulnerabilities. Again, more of a thing in a programming language like C, but for example, there are ways of using string operations in C that will continue reading code into unallocated memory space, which may or may not eventually result in a seg fault. This is a thing that's reasonably easy to pick up on if you know what you're looking for. Code review tools can help the process. So some of this knowledge can be encoded, and this knowledge that is encoded can be checked in a automated manner over programming code. We can have tools that show us vulnerabilities. This is called static analysis. There are formal code review methodologies. There's actually a reasonably large body of research that revolves around code review and all this sort of thing. The only drawback of this technique is that it can be very time-consuming. Anytime you ask a human to do anything, it's very time-consuming versus getting a computer to do it. Which is why computers will eventually replace all of humans. Computers also don't have to be paid, which is the other reason that computers are eventually going to replace all humans. So, Whitebox Techniques. So we can actually develop test cases with knowledge of the programming code in mind. So if your test cases don't cover all of the branches of your program, like imagine you've got, an if statement that has two if statements on either branch. If you want your code to be fully tested, each of those four branches needs to be executed at some point. However, it's impossible to know that you're not executing those branches unless you can look inside the code and see, oh, I'm not executing this branch. Also, static analysis. Run automated tools in order to find flaws in the program. For example, do I try to use a variable after it's been freed from memory? Is it possible for a counter to go past the end of an array? This is less relevant for Python than other languages like C, but still reasonably relevant. It's kind of like the parser that's attached to the Python interpreter, except rather than executing the code, it's looking for patterns in the code that correspond to problematic programming constructs. Okay, so let's see questions. Once again, as in all cases, if you have a problem with if you're experiencing something with respect to the grades, contact either me or Mark, and we'll sort it out. Okay, so debugging. Once your code has shown that your program doesn't behave as intended, or once your testing has shown that your program does not behave as intended, i.e. you have a bug, you gotta fix it. So, in order to fix the bug, you have to find the cause of the bug. So to find the cause of the bug, generally speaking, the thing you want to do is get your program to barf up as much information about its own business as you can. There is a precondition first, though. In order to know that the bug is, a problem and not just some transient artifact, you need a test case that reliably fails. When you see on these forums, and like bug report forums for like Dwarf Fortress and stuff like that, when people report a bug and the developer says something like could not reproduce, that means they could not find a test case that reliably repeats the problem that the user is describing. Yes. And in order to debug the program, you must try to understand the internal state of the algorithm. So, to understand the internal state of the algorithm, it's quite simple. You use print statements to print out potentially relevant variables, or you use a debugger to step through the program. So, let's see. Debuggers. There's, I think it's Python Tutor. Python Tutor. No. There's a, Python Tutor. Is it? Yes? I think this is it. Okay. Yeah, here we go. So, this is a website I highly recommend for debugging your Python code. pythontutor.com/visualize.html octothorpe mode equals edit. So, if we have, for example, a function that takes a list and an element, let's just do a for q in L, that will do a simple search function. If q is equal to e, return, or we'll do a count function. Count equals 0, count plus equals 1. Semicolons, I've been doing too much C. There we go, and then at the end we return count. So this just counts the number of a particular element in the list, right? If we then apply, gotta give it a name. Numbers, whatever. So if h is equal to, let's say, some sequence of ones and zeros, and we want to print the number of zeros, then visualize execution. So this is a tool that steps through your program one line at a time and tells you what the outputs are. So we have the global frame. Numbers is a function in the global frame, so numbers is now defined. We now have h in the global frame, which is defined. We then enter numbers. So we're now in numbers. L is this number, and E is this number. See how it's allowing you to visualize what the values of your variables are as the program is executing? This is very cool. So, count is now 0. For q in L, q is 0. If q is equal to E, count plus equals 1. Count is incremented. And then you can keep going. You can actually pull the slider through so you can see. There we go. And then it returns count. Return value is 14. Next, print output is 14. There you go. So that's super, super useful. pythontutor.com. Do that. Probably I'm going to look at the chat and see a bunch of people saying, well, this would have been useful on Saturday. And you're right. But, you know. If you put an infinite loop here, will it show the total number of steps? Probably not. So. Cool. Yes. Python Tutor. Python Tutor is super helpful. You know what? Probably if I were to like reformulate the course, I'd introduce it a little earlier because it probably would have been useful sooner. But anyway, but you know, this is the unit on testing and debugging, and that's the testing and debugging thing. Probably should just move this whole topic up. But anyway, in JHub there is one that's, I think, called Pixie or something that you can get, but yeah. Python Tutor. Do it. Okay. Anyway, that's our time for today. Thank you very much, everybody, for listening to me yapping on about miscellaneous things. We actually made pretty good time today. So, I will... Yes. Anyway. I highly recommend you guys... Oh, my goodness, I didn't even have my light on correctly this whole time. Yeah, so there are 100 gazillion of these Python visualizers that are sort of floating around. So if you have one that you like and prefer, please use it. But if you didn't even know these things existed, I recommend this one. It's nice, it's in the browser, you don't have, like, no muss, no fuss. It's very, and the this actually is interesting because it corresponds to the system call stack, which is like a more it's a methodologically rigorous way of viewing your information. So, how come tests get marked in a day but assignments take a week? Because for assignments we have we have the grace period until Wednesday. So we have to wait until Wednesday in order to mark them, otherwise people will be submitting on things that have been marked in the things released. So, programming is 10% writing code and 90% understanding why it's not working. Yes. I have a comic, actually, for you guys. Programming. Yeah, there we go. Here we go. Here's a comic for you. Thank you. Oh, that's rough. That is rough. Man. That's what, like... Okay. Quick, so quick piece of it, like, here's a good rule of thumb, for finding bugs in programs. The first thing you should check is that all of your variables are named correctly, and that you're not, like, 99% of the time, it's a stupid error like that. Like, you've misnamed something, or you put, like, you know, +1 where you shouldn't have, or you've got greater than when you meant less than, stuff like that. Yeah. Oh my god, that's true. Actually, that's interesting. The thing about bugs is fixing one bug might reveal the existence of additional bugs. So the sort of relation of number of bugs to the amount of time you've spent debugging can be nonlinear. Yep. Anyway, doesn't seem to be any questions. Vote Mark. Listen, Mark, if you want to beat me, then you're going to have to start coming up with your own memes, eh? Cool. Anyway, I'm going to sign off here. Thank you guys very much for attending class today. As long as it's socially distanced, okay? Social distancing. Yeah, so there are some URLs in assignments 9 and 10 that are currently broken, and we're on top of that, but we haven't done it yet because, like, we're not there yet. So, yeah, we'll have them fixed in time for you guys to complete the assignments. Don't worry. Okay. So anyway, take her easy, folks. Don't do anything I wouldn't do.